In this video we're going to be talking about the third and last of our vector products. This is called the cross product, and in this version, a cross product, you take a three-dimensional vector, do the cross product of that with another three-dimensional vector, and you end up with a three-dimensional vector for the output. Notice that whereas the scalar multiplication, scalar times vector equals vector, and dot product, vector times vector equals scalar, both of those can be done with any dimensional vector, like 2 dimensions, 3 dimensions, or any dimension like 13 or 15 or 25. The cross product is only going to be defined for a 3-dimensional vector times a 3-dimensional vector gives you a 3-dimensional vector. Now, the first thing I want to talk about is these unit vectors. The vector I is the vector 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So they point along the x, y, and z axes, the positive parts of the x, y, and z axes, respectively. And they have length 1, so they're called unit direction vectors. Now, sometimes you'll see a vector written in component form like this. So if you see the vector 3, 1, 2, for example, I'll normally write it like this, but you might see it written as 3i plus 1j plus 2k. So sometimes you'll see vectors actually written that way. Okay, so let's go back to this. And when we do a cross product of u and v, let's say u is u1, u2, u3, that's the x, y, and z components. V1 is V is V1, V2, V3, again x, y, and z components. So think of the first component as delta x, how much you change in the x direction, think like east-west. And V is how much you change in the y direction, like say north-south. And then V is how much, or the third component is how much you change in a third direction, up and down, for example, in the z direction. Now, the formula for doing this is a little bit more complicated than the formula for the dot product and the cross and the scalar multiplications, which are pretty simple. But here, what you do is you write your vector, write your unit vectors I, j, and k, and then you write your components of your vector u, u1, u2, u3, and in the next row you write your components of v, v1, v2, v3, and then you recopy the first two columns here. So we've got a total of 5 columns here, with the last two being the same as the first two. And then what we do is we multiply along a diagonal. So you can see these, the ones that I have highlighted in blue here, so those are the ones, actually it says positive, that should say negative. They have a negative slope, and these have a positive slope. Okay, as you can see here. And so the ones that are going down and to the left, those will be added, and the ones going up and to the right will be subtracted. And notice that you are going to have one each for I, j, and k that are blue, and one each that are red for I, j, and k. And so we're going to get it, it's going to work like this. So for the I, you're going to have a u2 times a v3 times the I, minus a u3 times the v2 right here for times the I. Okay, and for the j, you're going to have a u3 times v1 minus these two, u1 times v3. And for k, we're going to have a u1 v2 minus the u2 v1. So here they are, and if you put the i's together, that's the first component. And put the j's together, that's the second component, and the k's together, there's the third component. And to me, this is the easiest way to sort of remember how to do this one. Okay, and we'll do this with some numbers in a subsequent video. But notice what's happening is, to get the I component, the first component, notice it does not use the I components of either u or v. It deals with the other two. It deals with u2, u3, v2, and v3. And notice you have u2, v3 minus u3, v2. And notice that the if you do these in u's first, then v's, then they're in increasing order here and the decreasing order for the minus. Same way for the last one here, for the last component, the k, the k component, the z component, the third component here. Notice it doesn't have anything to do with the u3 or v3. It only uses u1, u2, v1, and v2. And again, if you put them in alphabetical order, uv, it starts by going 1, 2, and then the minus 2, 1. But the one in the middle, the sign is back, the order is backwards here, because if you put them in order from uv, it goes 3, 1, then minus 1, 3. So this one is in decreasing order here for the first one, whether it's increasing order for the others. So if that helps, if you just want to memorize the formula, you can just memorize that, or you can, to me, it's easier to do this little process up here. But either way you go, there's this is how you come up with it. So it's a little bit more complicated, but you do have this sort of cross thing going here, where you're taking the components and sort of cross multiplying there. Okay. Well, alright, so you've got this semi-complicated thing here. How do we interpret it geometrically? Well, first of all, let's determine the direction of this vector. And notice that if we dot u with the cross product, so here's our cross product we just defined right here, and here's the vector u, and we do the dot product. Well, you're going to distribute here and here. But if you look, the two blue parts cancel, the two green parts cancel, and the two black parts cancel, so that you get a dot product of 0. Similarly, if you do v dot u cross v, same kind of process here. You see that the blues cancel, the greens cancel, and the blacks cancel, and so when it's all said and done, the dot product is 0. Now remember, one of the things that we discussed about the dot product is, if the dot product is 0, that means that the two vectors are perpendicular to each other. So, here in boldface is the conclusion that you want to remember, is that the cross product is perpendicular to both u and v. So, when you draw the two vectors u and v, there's always going to be some plane that contains both of them, and the cross product is going to be perpendicular to that. Now, there's actually two different directions that could be. Think if you draw on a board, let's say a whiteboard, and you draw two vectors, okay, then you could either be pointing straight out of the board towards you or straight out of the board away from you, okay, and so there are two different ones to choose from. We can choose between them with what's called the right hand rule. So what you can do is you can place your fingers of your right hand pointing along the first vector. Say if you're doing u cross v, you would put your fingers across in the direction of u, rotate them in the direction of v. So turn your hand so that you could rotate. When you close your hand, you're rotating your fingers in the direction from u to v. And when you do that, then your thumb will be perpendicular to that rotation. That will be the direction of the cross product. Okay? Now, the magnitude of this turns out to be the norm of u times the norm of v times the sine of the angle in between. Now remember that the cosine, that the dot product was the norm of u times the norm of v times the cosine of the angle. And so it has something to do with these projections. Okay? So we found that the dot product was norm of u times cosine of theta, okay, was the magnitude of the component of u in the direction of v. Well, similarly, we see that norm of u times sine of theta is the magnitude of the component perpendicular to v. So what we're basically doing is taking those two components and then just multiplying them by the size of the vector v to get the size of the, in one case, the size of the dot product, in the other case, the size of the cross product. Okay? And so that's the basic interpretation. So we need to follow this up with some examples, and so I'll follow that up in a minute. In the meantime, let me just draw a couple things here by hand. So if you have some vectors going here, say this is u and this is v, then let's pick a different color. And there's a vector in this direction. Let me call that H. Okay. And let's take another vector in this direction. I'll just call that A. Okay. Well, we'll call the size of it A and the size of that vector H. Of course, the size of this vector here is norm of u, and the size of this vector is norm of v. So, and of course, horizontal may be off here somewhere. Okay. Well, it turns out that we saw earlier that the size of A is going to be H. Well, size of A. Wait a minute. Let's say that again. If we do this, and we'll call this angle theta right here between the two. So if we do the sine of angle theta, that is A over H, over the norm of u. So the height of this distance here is norm of u times sine of the angle theta. But wait a minute, if we look at this length is norm of v. So if we do the norm of the cross product, we get norm of v times the norm of u times the sine of the angle in between, and that turns out to be the same as if we extend this out parallel and we find the area of this parallelogram, remember it's just base times height. Well, this is base and this is height. So this is the area of the orange parallelogram. So one way we can think of the cross product is the area of that parallelogram. Another way we can think of it is if this v is 1, so if you cross product with a unit vector in the direction of v, then it's just the height of this vector here that's going in the perpendicular. So that's perpendicular there, so perpendicular way. Or you can take that red vector then, take the length of that red vector, okay, and then multiply it by the length of this base vector v. Okay, and that's the size of the cross product. On the other hand, if you're looking at the dot product, remember, was norm of u, let's see, I'll do v first, norm of v, norm of u, times the cosine of the angle in between. Well, this norm of u times the cosine of the angle in between, well, let's look at the picture. Cosine of the angle in between is a over u. Okay? So, a over the norm of u. So, u times this is the length a, the blue length, and that's times the vector v. So, the dot product can be thought of as basically the length of that vector times the length of vector v. So, when the two vectors here and here they happen to be perpendicular, this blue one gets to be 0, and so the dot product is 0. Okay? Now, what about, and then the h is just the norm of u. So if the vectors are perpendicular to each other, then the sine of theta is 1, and so you're just multiplying the two lengths of the vectors. But as the angle gets smaller or further away from perpendicular, either it could be obtuse or acute, then we're getting smaller. So in other words, the biggest you can make this, another way to think of it is the biggest you can make this for a particular length, the biggest you can make the parallelogram is as if it's a rectangle. But if you take this, say, and swing it around and make a parallelogram like this, now it's smaller. Okay, and so the cross product is getting smaller as that angle theta gets closer to, well, to horizontal, either closer to pi or closer to 0. Okay? In contrast, the dot product can be thought of this way. If the two vectors are going in the same direction, then the angle is 0, and so that part is just 1, and you're just multiplying the two vector lengths together. Okay? If the cross product is going to be positive anytime you have an acute, the dot product is going to be positive anytime the angle is acute between the two, and if it's an obtuse angle like this between, say, U and V, then you get a negative dot product. And of course, when you have this negative dot product, you're going to be having the blue vector is going to be pointing away from V, and the I guess I've made it red here. The red vector, that's your H, is going to be pointing, of course, still perpendicular to the vector V. Okay, so both the dot product and the cross product have something to do with the sizes of these components here and here. The horizontal component is basically controlled by the dot product, or it's sort of dot product sort of measures that in a way. It measures the size of it, but then it's times the vector V. And in the red one, the perpendicular component is basically the size of the the size of the cross product is the size of that perpendicular component times the size of the vector V. The size of the parallel component is there, and if you multiply that by the size of the vector V, you get the dot product. Okay, realizing this is going to be a negative number when you have the angle between is acute. Okay, so that gives you an idea, another way you can think of both the cross product and the dot product geometrically, and then of course we also have found out these ways of computing them. So the next video is going to come in, and I'm going to show a 3D example, and it'll be work with this a little bit, so we'll get to practice working with some specific numbers with the 3D times 3D, and we'll look at scalar multiplication, dot product, and cross product for a specific example.